Hey people. Hey, the last time we looked at the theory behind acid and base. And we looked at a couple of dudes. 3 dudes actually. The first dude, Arrhenius, says acids, generates H plus and bases generate OH minus. His name is Arrhenius. But the problem with Arrhenius is that H plus is too unstable to exist. OH minus, well, there's certain base that doesn't always have OH minus. So he was kind of stuck. Then we have Bronsted and Lowy. They gave a better idea. He said that, an acid are proton donors. Okay, they donate H's so water can pick them up when water decided to act like a base. Whereas a base is a proton acceptor. It accepts an H from water, where water will now act as an acid. So if this is still confusing you, I would recommend that you go back and watch, the latter part of the video. I wouldn't watch the whole thing. That whole thing is like 40 minutes long. I'm sorry for making it so long. But there's just a lot of things to talk about. It is topic 8 if you think about it. Now, let's take a look at strong acid versus weak acid today. So today's lesson is about strong versus weak. And we're going to look at something called conjugate pairs at the very, very end. So what makes an acid strong and what makes an acid weak? Well, let's kind of determine this first. Okay? These are all strong acid. These are all acids that are strong, meaning that they will have a pH of around 1, meaning that these guys can definitely hurt you if under a very, very high concentration. Okay? They will take water out of your skin cells, okay, and give you a burn, kind of like firewood. Instead, fire evaporates the water out of your cell. These are chemically taking water out of your cells to make H3O, which is something that we learned last time. So what do we have here? Perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and oh my goodness, sulfuric acid. This guy is dangerous, man. Okay, some of them, of course, this one, they're all monoprotic. Okay, sulfuric acid is the only diprotic. Okay, and we mentioned what they mean last time. So if you don't remember, again, just maybe go back and take a look. But these are all strong acid. What do you mean strong? What makes them so strong? It's almost like saying, what makes Mr. Lung so strong? Well, let's take a look at this. We've seen this diagram so many times. HCl. It's Lewis structure. Okay? When you put HCl in water, it will dissociate. Right? We know that. Because that's what water have the ability to do. Dissociate acid. Well, in terms of strong acid, it will dissociate completely. Strong acid are completely dissociated. Now, what does that mean? Let's say you have 5 of these. Okay, you have 5 HCl. And you're going to drop them all in water. What happens? Well, you're going to get 5 H pluses or 5 H3O plus. Remember, H plus doesn't really exist, but what exists is H3O. But remember, we also say the concentration of H plus is equal to the concentration of H3O plus because they're really the same. and 5 Cl minus. So it's almost like saying, now you have 5 married coupled right here. Happily married couple, kinda. Okay? When they meet water, they all got into a divorce because strong acid has a 100% dissociation. Completely dissociated, completely ionized. If you have 10 of these, you'll have 10 H+. If you have 50 of these, you'll have 50 H+. Because that's what acid do. They completely dissociate. Okay? HCl does this. HNO3 does this. HI does this. HClO4 does this. But what about the others? Okay? What about the others? Well, let's kind of just write this in for now. HCl plus H2O will give you H3O plus and Cl minus. Okay, let's write that in for now. But what about weak acid? Because it is stated right here that if you're not part of the elite 6, you are weak. If you're not part of this group right here, you are unable to dissociate completely. Whoa, what do you mean by that? Let's take a look at another acid. This is a weak acid example. Right here, this is a weak acid example, which I already gave you the reaction for. Let's call this weak acid HY. Okay, doesn't matter what it is. This is not a real acid, it's just HY. Okay, it's a weak acid. And here's water. I'm going to drop this acid in water. And let's say there's 5 of these. Okay. Now, remember, if it's strong acid, it will have a 100% dissociation. Meaning that if it's a weak acid, it will not be 100% dissociation. I don't know. Let's say this dissociation is only 20% dissociation. Could be less. It could be more. But if it's not 100%, it is weak. Okay? It is weak. So if this guy has a 20% dissociation, what are you going to see in this beaker of solution? Well, there's 5 of these things, right? If only 20% of the 5 gets dissociated, that's pretty weak because you're just going to have 1 of these. I hope my math is right. Which means, what about the other 4? The other 4 will still be married together. Okay? That's 20% dissociation. Obviously, if this was 50% dissociation, well, it can't be, right? It's going to be really strange. But let's say it's like a 25% association, or I don't know what, that's not gonna work. Maybe I shouldn't have put 5. That's a bad number. Yeah, but you get the idea. Okay? So that's the difference between weak and strong acid. Strong acid, it dissociates completely. Everybody get into a divorce. Whereas a weak acid, as you can see right here, depending on the dissociation percentage, some of them get into a divorce, not all. And that's what makes a weak acid weak. Okay? Later on, we're going to be calculating something called pH. Okay? pH is a rating. Okay? It's a rating showing how much H's are there in solution. The more H's there are, the lower the pH. That means the stronger, the more acidic it is. Okay? We can see how this is a strong acid because it has lots of H. It is these H's that makes an acid acidic. If you look at a weak acid, look, it generates less H. And that's what makes it weak. Because there's less of these to turn water into hydronium. Okay? So you'll learn that next class, where we see that pH is actually equal to the negative log of H plus concentration. Okay? The more of these there are, the lower the pH. That's why strong acid tends to have a lower pH versus weak acid, because they don't completely dissociate. Hopefully you sort of understand what I just said there. Okay, so note, okay, the water molecule actually takes part in the chemical reaction. We know that. It accepts the hydrogen ion from the acid, and we also know that because water is acting like a base. It's accepting these guys to form H3O. All right. I guess I really shouldn't put that here. This diagram right here should have been down here. Let's make sure you draw it down here. Okay, because HY right here is really just an abbreviation of a strong acid. But it's really the same anyways, no big deal. Okay. All right, strong base versus weak base. Okay. We know that strong bases highly dissociate in water to form what we call hydroxides, which is OH minus. Okay, and here are some strong bases that you have to keep in mind. Sodium hydroxide, potassium hydroxide, lithium hydroxide, and barium hydroxides. These guys, when immersed in water, will completely dissociate to give you Na plus and OH minus. So if there's 10 of these, you'll get 10 of these. Okay? So just like an acid, if you're not part of these elite 4, you are weak. As simple as that, and exactly what we've mentioned earlier. Okay? Because weak bases, they don't fully dissociate. So the diagram is exactly what we saw before. Okay? All right. We'll do this next class. Okay, looking at pH and looking at these mathematical expression. But I want you guys to turn the page. Okay, I want you to turn to this page right here. Oh, I think I went too far. It's supposed to be 190. Right here. Okay, conjugate pairs. So now that we know the difference between a weak acid versus a strong acid, let's take a look at conjugate pairs. Okay. Oh, let me do one more thing first. Let's go back to weak acid. Oh, this is actually very important. Okay. This is actually very important. What makes an acid weak? Well, why is it dissociate incompletely? So let's say let's do an example, because there's an example. I should give you an example here. Okay. This is an example of a weak acid. Let's not make it so complicated. HF is a weak acid. Hydrofluoric acid. Okay. Hydrofluoric acid will react with water to create H3O plus and F minus. Okay. Why is it weak? It's because when this guy reacts with water, it doesn't completely dissociate. It's this situation right here. You take the Y and turn it to an F. That's exactly what happens. Okay? Now, why does it incompletely dissociate? Why don't all of these get into a divorce? It's because for all weak acid reaction, there is an equilibrium. Okay? The reaction can go backwards. What that means is that even if I have 5 of these and I make 5 of these, but for some reason due to the condition, this reaction can go back. Meaning lowering this number to maybe 2, and this go back to 3. Because this reaction right here can always go backwards. That's what a weak acid. That's why weak acids are weak. Okay? Because these guys doesn't just only go forward, but it has the ability to go backwards. Now, that's why. Whereas a strong acid will only go forward. Once it makes H3O and Cl minus, it actually doesn't go back and become HCl again. Meaning there's lots of these guys persisting in your solution, creating a very low pH. Okay? All right. With that in mind, I'm glad I remembered to tell you this. Let's go back to this page right here, called conjugate pairs. All right. So Bronsted acid and base systems involve two acid base pair. Okay, the trick here is water. We saw in the last class that water is amphiprotic. What that means is that water can act as an acid or it can act as a base depending on who he's dancing with. The missing word here is hydrogen. Because you have to look at hydrogen. Hydrogen is the key in determining if something is an acid or a base. In this case, conjugate acid or conjugate base. Because the difference between the two is by one hydrogen atom. Okay? And the term conjugate is usually talking about the right side of the reaction arrow. Okay? And is usually based on reaction that can go backwards. Which means for the first example right here, if you were to predict a product, it would be H3O plus NO3. Okay, this is nitric acid. It's actually a strong acid. If that is immersed in water, being the proton donor that he is, he will donate his proton to H2O to become H3O. Proton donor, proton acceptor, acid, base. You see what I did there? Okay, this is an acid. This water right here is acting as a base. Because this water right here is taking this H away. Proton acceptor, right? Acceptor. Okay? Makes me basic. Okay? Proton donor, right? Donor. Makes me an acid. Now, for this reaction, there will be no conjugate acid and conjugate base. Why? Because H3O will not go back to become H2O. NO3 will not go back to become HNO3. Because this is a strong acid and this has a 100% dissociation. You have 5 of these, you're going to get 5 of these. Okay? However, not this one. The next reaction is based on a weak acid. This is called acetic acid. This is your vinegar, guys. What you get right here is H3O plus CH3COO minus. That's what you're going to get. Okay? We can see that this will donate an H to H2O to give you H3O. So obviously, HCH3COO is acting as an acid. H2O is accepting this H to become H3O. which means H2O is acting as a base. Okay? Now, the difference in this reaction is this. This guy is a weak acid. This is vinegar. It's not part of the Elite 6 that we learned about 10 minutes ago. So what that means is that this reaction can go backwards. Okay? If it goes as backward, we have to look at it as being backwards. So let's look at things backwards. H3O reacts with CH3COO. Okay, H3O is reacting with this to go backwards. What that means is that H3O will donate an H to CH3COO, right? H3O will donate one of these to here to create this. He lost an H to become this. He lost an H to become this. Doesn't make him a donor. He's going to donate one of these H's to acetate. He's an acid. He's a proton donor. He's going to donate one of these H's. Right? So H3O in a sense of a weak acid, acetic acid in this case, is actually an acid. But not to be confused with this acid, we're going to call him conjugate acid. So H3O is a conjugate acid of acetic acid. This guy right here accepts an H, accepts an H to become acetic acid. So this guy is a base. Not to be mistaken with this base, he's a conjugate base. Whew. So the fact that you have to keep in mind proton donor, proton donor, proton acceptor, to understand this. Okay, looking at the fate. What happens to H3O if it goes backward? Well, H3O becomes H2O. To do that, it lost an H. That's a proton donor, if you think about it. That's an acid. Being on the right side is a conjugate acid. Okay? Now, to finish, there's something that I'm going to have to tell you. An acid in its conjugate base is called conjugate pairs. Okay? It's called conjugate pairs. Base and its conjugate acid is also known as conjugate pairs. Okay, so when you look at an acid and its respective conjugate base, it's always one hydrogen less. Right? This and this has one hydrogen less. This is a very, very important concept, especially those of you who are in HL chemistry. Very important concept. In fact, even though if you're in SL chemistry, but you're looking at HL biology, this is also an important concept. Okay? But we'll tell you later on what that important concept is. All right, let's take a look at these guys. Okay? You can see the fact that these guys are all weak. Okay? They're either weak acids or weak bases. How do I know? Well, I try to draw the equilibrium sign. It looked more like a resonance sign than anything else, if you remember resonance. No? All right, so let's take a look at these things. HCN's fate is to lose this H to H2O. What that means is that you're going to be an acid. Water will act as a base. Okay? Well, cyanic acid is definitely a weak acid because it's not part of the elite six. So what that means is that these two can get together and go backwards. So let's take a look at H3O. H3O will lose one of its H's to CN to become HCN. You're going to lose, you're going to be an acid. And because you're going backwards, we call you a conjugate acid, which means this is going to be a conjugate base because he's a proton acceptor. All right? Next example. Okay, so the whole idea here is identify who is the acid and who is the base, who is the conjugate acid and who is the conjugate base. So here I have carbonate, okay, reacting with water. Well, it looks like that the fate of carbonate is to become bicarbonate. To do that, I'm going to have to accept an H. Ooh, proton acceptor, huh? I must be a base. Water in this case is acting as an acid then. Okay, remember, water is amphiprotic. Okay, this reaction can go backwards. So as going backwards, the fate of bicarbonate is to become carbonate by losing this. It's going to donate that, which makes this an acid. Conjugate acid. This obviously accepts the H to become H2O, so it's a conjugate base. Okay, one more and then we'll call it for the day. NH3. Okay, ammonia reacting with water, and we've seen this before, that NH3's fate is to become NH4. To do that, I'm going to have to accept an H from water. Hey, being a proton acceptor, I am a base, which makes water an acid. Again, going backwards, NH4 becomes NH3 by donating one of these. Donating? I guess I'm a conjugate acid, which makes OH, the proton acceptor, to become H2O, a conjugate base. Okay, and be able, of course, to identify the conjugate pairs for these reactions. And that's pretty much it in terms of strong acid versus weak acid, conjugate pairs. And for the next class, we're going to start looking at numbers again by looking at pH calculation. I need you to have a calculator, and your calculator needs to have this function called log, because without it, you're not going to be able to do these pH calculation. I doubt you can do log on paper, or it's funny, do log in your head. All right, let's call it a day. Bye, guys.